I'm Garrett Babon. I work at Microsoft as an architect, dev kind of person, and work in Azure Storage. And my coworker Madhav is here with me, Madhav Pandya. And yeah, I wanted to talk about our title here, Efficient Media Utilization Across Dissimilar Cloud Storage Systems, kind of a mouthful. But we really want to talk about kind of a journey that Madhav and I have been on for the last few years here, trying to make efficient use of our media, but we have two main systems, so trying to figure out a way to do that in a cost-effective way. So yeah, let's get going here. Quick agenda run through. I want to go over some background information just so we're all kind of talking about the same thing, you know, once I reference things, what I'm referring to. And then really want to talk about the effects of layering. This was a big part of what Madhav and I discovered that was kind of affected all of our decision making and what we had to kind of keep in mind throughout the process. Talk about new media types, and when I talk about new, just to be clear, I'm not talking about new in the case of like the silica stuff, like, you know, crazy stuff. This is new is where things we can actually get our hands on today, but we haven't been using for like the last 20 years. So it's just, you know, ZNS drives, SMR drives, that kind of stuff. And not really going to dive into it, just again, kind of set the framework for how we think about it. And then the real part I want to get to is our new object store. So we came up with a new way that we're storing our data on the actual nodes at the lower layer. And then our new development platform that was kind of a, we didn't want to have a lot of code bases. So again, efficiency, not just in media utilization, but efficiency in our own development efforts. And then just kind of wrap things up. So with that, background information. So this is just a very, very, very high-level diagram of our append-only system that we use in Azure. This is kind of the workhorse of Azure Storage. We have a log-structured merge tree. For me personally, it's kind of a log-structured magic tree. I don't really know how those things work exactly. That's not my wheelhouse. But its assumption is that it's writing over an append-only store. So that's the kind of stuff that I was working on in the past and still work on to some extent. So the append-only store that we have is where we actually get our durability in Azure. This thing does all the replications and erasure coding and all of the fancy stuff that we do. And the log structure merge tree doesn't have to worry about that stuff. And then we have our media underneath that. And so this is how we do like keys, values, files, like you can kind of put really anything into this blob storage. And that's, like I say, kind of I consider the main system of storage. We also have our newer system, which is our update in place store. And this is primarily used for virtual disks. And this one you can see just has one less layer. So we just have an update in place store. That's where getting all our durability, triple replication, whatever, all the same kind of things that you would normally do to make sure that your data is nice and secure. And it obviously talks to the media. And so this is optimized for updating data in place from the client's perspective. But actually, it uses update in place pretty much throughout the entire stack, except for at the very bottom, which we'll get into a little bit. The other topic I want to talk about is indirection versus redirection. And these are kind of my terms for this. This isn't exactly, I don't know, maybe Webster would agree or something. So I mean, but I just wanted to cover the way we think about these things, and it's a key part of the rest of the discussion. So with indirection, the idea here is this is the classic thing as the flash translation layer, the FTL inside of an SSD, where you're giving somebody the illusion that they're updating something, but in reality you're writing it somewhere else. They're updating in place. So it's logical block addressed to a physical location somewhere. So that's the classic use of that. Very dynamic because you're every time that a write happens, typically in this scenario, it'll change whatever that database thing is. It requires some additional storage and updates to that. The centralized brain, whatever that thing is, it has to be part of the system and constantly being referenced and updated. It does give you this huge freedom, which is you can kind of place your data anywhere. As I used to tell my boss, it's like writes are easy, reads are hard, because with writes, I can put the data anywhere as long as I remember where I put it. But when I go to read it, I have to remember where I put it and I have to go get it from there. So this is what allows you to do that kind of thing. There's also a concept of redirection, which I don't think it's used quite as much anymore, but it's a very old concept, obviously, which is like what RAIDs would do and things like that, where you just have fixed offsets Like I'm going to put the first megabyte on this unit, and then the next megabyte here, and the next one here, and you just kind of rotate through. So it's just math. It's just, and you can use whatever you want, some stripe size, some whatever, and you figure out whatever that formula is. You plug in like a logical block address, and it's going to spit out some location. So what's nice about this is it allows for a shared understanding of where the data is. Instead of having that centralized location, if we all just agree on where the data is going to end up based on this input, it's going to end up here, we can all share that information, not have to keep going through some centralized place. But that also forces where the data is going to be, because we've all agreed where the data is going to be, so it better be there. And then I did a couple little visuals here, just try to make it a little clearer. So this is just a super, super high level idea of indirection where the client view is up there. I just have A, B, C, D, E, F, G, H. I've got some type of mapping database. Doesn't matter what it is. It could be a tree, it could be a linked list or whatever, right? But it's some type of thing that says, okay, this is where your data is. So when you want to actually access it, so in this case, I'm trying to access E, I have to go look that up. So this thing's going to do some type of search through whatever that is. It's going to find it and go, oh, that was actually put over here. And if there was an update, obviously that could change. And so every time I have to go do this update. So this is, the kind of this log structure merge tree, or like say a flash translation layer. That's what they do. This is what redirection looks like, which is same client view, A, B, C, D, E, F, G, H, but we just have this idea of we know what the math is like. We know what basically based on this input of a location, where it's going to end up. Everybody can agree on that. So in that exact same scenario, we say like, okay, I want to access E. I don't have to do anything other than just go directly to it, because I can do that math myself, and everybody can do that. So that is kind of like, say, the background I want to give you. We have an update in place system as well as our append-only system, and we use both indirection and redirection. So why does that matter for this? So the effects of layering, this is where Manav and I spent a lot of time thinking about things, probably too much time. So back to that log structured merge tree, our indirection layer is in that log structured merge tree. It does exactly what I was just saying there. If somebody goes and updates some data, they'll say, oh, this was A, I'm changing it to B. It actually gets written in a log structured format to somewhere else. We update where that is, and then the durability is handled by that layer below. So that's the thing that actually replicates it. And we can do all kinds of fancy stuff down there. We use all kinds of erasure coding and things to make sure that we have efficient use of that. But we did have a problem, unfortunately, is there actually is another layer of indirection down there that we really don't need exactly, and that is the flash translation layer of Flash, if you're on Flash media. If we're on spinning media, a conventional hard drive, you actually don't have that layer, and way back when we started, we didn't, but obviously Flash is predominant media right now, so we do have that indirection, and when you have multiple layers of indirection, the write amplification factor goes way up, as I'm sure you guys are familiar. It's multiplicative. So if you have, a WAF of 2 at the top and 2 at the bottom, you have 4. So we do a lot of work to keep our indirection as low as possible in our log structured merge tree, and we do a great job of that. But it gets multiplied by whatever. Even if you have it low, it still gets multiplied. So one of the goals that we had was to say, we want to try to get rid of this indirection at the lower layer. That was one of the design goals where Madhav and I started working on saying, okay, how do we eliminate that? But we had another wrinkle to that, which is we have our update in place system. So this has durability above the indirection. So this uses that redirection logic we were talking about that says, okay, I've got this block of data. I know where that data is, and I can go directly to it. So that then jumps to one of these things that does the durability and does replication. But again, we can't move that data around exactly. We have some ways we can do that for like rebuild and failures and stuff. But in the general case, the standard I/O case, data is at a fixed location. And what we rely on is the indirection in the actual media. So this system needs indirection in the media. So if we just said, well, we're going to use media that doesn't have indirection, then the system doesn't work. And so one option is to say, well, let's just keep 2 completely separate systems that have no commonality between them. But that isn't efficient for a variety of reasons, as far as, okay, I have to buy 2 different types of everything. I have 2 different code bases, all that stuff. So then we were like, all right, how do we have both systems run on a common platform? And so that's what we were trying to do. So this is just kind of talking about what I was saying there. Indirection on top of durability, that was the append-only, just lends itself to append-only. Oh yeah, one point there, efficient snapshots. One of the nice things about like log-structured merge trees is, or really any type of append system is you have garbage collection. Snapshots are pretty easy because you say, well, I just won't garbage collect that. Someone's still using it, so I won't get rid of it. Downside is it does have this single brain thing, wherever that centralized thing, that database we have to go look through, so that can reduce performance. We have a single point of failure. You have to fix all of those things, partition it, have shards of this, have recovery systems, things like that. Because of the fact that we're abstracting how the data is actually stored, it does make it easier for us to do things like erasure coding, because we can move things around and underneath the system from the client's view. On the other one, where we have durability on top of indirection, that's our update in place system, lends itself to that. It's inefficient snapshots, quite frankly, right? Like when you go to take a snapshot, you have all this data stored, and you're like, well, but I update it in place, so I actually have to go put that data somewhere else. So that gets complex. But because of the direct access, again, we're doing redirection, where we just say, oh, this block of data is there, and we can just go directly to it and go access that data, whether for read or write. We get pretty high performance from that. But that limits where we can place the data because everybody knows where the data is. And then like we talked about, if you have multiple layers of indirection, it's just bad. WAF goes up a lot. So new media types. And again, new is newish. This is just a high-level overview, just so we're all on the same page and we're all like, know what we're talking about here. So conventional SSD, this is my representation of it. You have an IO stream. By IO stream, I mean you can do reads and writes to it. You have some indirection layer. In this case, that is our flash translation layer. And then there's a whole bunch of zones that are written to that are completely hidden from us. And we can treat this drive like we can read and write to it randomly. It does all the heavy lifting for us. Been using those, still use those, great product. FTP SSDs are a newer one. Yeah, by the way, that's not new. The FTP SSDs, flexible data placement, this expands on that and says, okay, I'm going to create multiple IO streams. I'm still going to have an indirection layer. I'm going to still kind of hide the zones from you and allow you to update in place and do that kind of thing. But it allows you to separate the data. And you can use that to reduce WAF quite a bit, because you can group data by lifetime, and that really helps. That is a really good thing. We're not going down that path. We're using the bottom two here. So we have ZNS SSDs, and I changed this to right pointer because we are able to access the zones directly. So we're basically writing an append-only mechanism to the actual drive. We cannot update and rewrite anything. We have to complete the zone. We then seal it, and then you can read it. And then when we're done, we can erase it, and then you can start over again. So we have to do all of the work ourselves as far as indirection on top of this. But that gives us the most advantage. SMR hard drives, the shingled magnetic recording, just in case somebody doesn't know the thing, it's just a way to write conventional, just writes tracks next to each other, single layers them, but it has the exact same properties as a zone namespace drive, which is you have to write from beginning to end sequentially. You can read from it, but in order to rewrite again, you have to erase. They call them bands. We're still just calling it zones, bands, whatever, groups of things. Kind of doesn't matter what we call it. So those are the media types that we generally use. So a little bit about the ZNS drives and why we're going down that road is it's less RAM and over-provisioning in the drive. It saves us a bunch of money, right? And since we don't have the drive doing indirection for us, we can say, you don't need to do that. We'll take care of it. So don't put in the stuff that needs to do that. And so we can get a reduced cost from the drive. But it does require an indirection layer above it because, again, my life would be so much easier if everybody in the world just like wrote 256 megabyte chunks of data sequentially, read them and deleted them, right? Then you really wouldn't need any of this. But the reality is everybody says, okay, I'm gonna store a picture of my food and send it to my friend and then delete. Like it's just all that stuff that's happening up here, but we have to somehow distill that down to these like 256 megabyte sequential writes. So we have to add that indirection layer, and that adds cost, mainly from development support, all those kinds of things. It's not a cost of of operations or even purchasing, but a cost of development and supporting. And that's why scale is an important factor, and that's why we're in the cloud track or whatever for here, is that if you're buying, I don't know, 100 drives, I probably wouldn't go down this road because you're not gonna, building this layer is not cheap. And so like if you're, I'm making up numbers, I'm gonna be very clear here, I'm not talking real numbers, but as an example, if you were saving like $5 a drive and you're buying 100 drives, $500, I'm not gonna build you a flash translation layer for $500. But if you're buying 100 million drives, right, all of a sudden that's a lot of money, right? And now I can afford to go do that work. So, and none of those numbers are real, very clear about that. And then, yeah, and so the other advantage is it allows for specialized indirection, and we'll talk about that a little bit here in a second. Shingled magnetic recording drives, SMR drives. We're also using these very similar to ZNS, exact same properties. And you can have a conventional area. What's nice about the conventional area on the SMR drive is that by doing just conventional recording with the tracks next to it, you get that ability to overwrite data, and you don't need an indirection layer. So there's a little cost in that you're less efficient for that one area of the drive. But there really isn't, there's no over-provisioning, there's no RAM, there's no logic in the drive. It's just writing in the traditional way that a drive would write. And so that allows for some easier implementation of some traditional file systems. It just gives you a place where you can squirrel away some data that you can overwrite, which is convenient. The ZNS drives don't have that. But the shingled area does require that same indirection. I made a note here, just we only deal with like the host managed drives. There are the drive managed, but we aren't going down that road. So we have to do the indirection ourselves. As I said, it's very expensive to develop that, but once it's developed, you can save a tremendous amount of money using an SMR drive. And I'm gonna take one moment here to just make another point I didn't really put in the slide, which is one of the things that Madhav and I have been doing with this is, and that's kind of part of the talk, is looking for similarities between things and how to utilize that. So instead of thinking of like, oh, I've got this hard drive which is spinning and it's got shingles and blah, 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 and then I've got my ZNS, SSD, which is flash, and it's got planes, and there's radically different things, which they are, but the interface to them actually looks almost exactly the same. And so how can we utilize that similarity when we're writing our code rather than thinking of them as separate things? So, which leads to this, our new object store. So this is where we're actually doing our, the most of our work right now, our work. And the key to it was, it's gonna provide both update in place and append-only objects. Because we have our append-only system and we have our update in place system. So how do we do that is what we'll get into, but being able to offer both of those in one system was the key that allowed us to converge these. And say, instead of having to run two separate systems, I can have one system that at the lower layer is optimized for both. So we're building it on ZNS and SMR. You can work with conventional devices. It's, we can always sit on top of that. We don't have a hard dependency on those. And another big feature that we put in was abstracting the media type. And this again gets into looking for the similarities rather than the differences. Is where you say, all right, an SMR hard drive and a ZNS SSD have these similarities, they have these differences. How do we represent that in an abstract way? How can we then use that with a conventional SSD? So simple example would be, we have zones and bands. We just represent that as, I think we're calling it an erase unit, basically, where you have this unit that you write to, that you have to write to sequentially, and then you can erase it. But then we can have other properties like, do you have a seek penalty? So there's a seek penalty on a spinning media because the drive has to move. There isn't a seek penalty on an SSD because it can access the flash directly. So being able to just kind of abstract those out and then have the upper layer just query for properties and adjust its behavior slightly based on what's underneath it allows us to not have to build these separate things like this is our SMR stack and this is our ZNS stack. We can build one stack that just tunes itself a little bit based on the properties of the media underneath it. Optional indirection. That was basically the key feature that allows the top one. So when you need indirection, you turn it on and you say, this object, I want indirection. I want to be able to update this thing in place and you do all of the heavy work for me. If you don't need that, it's like, I have my own indirection above me, give me an append-only stream that I'm gonna write to and don't do anything, it'll allow for that. I also put in here that we support compression natively. This kind of gets into that, like having your own indirection layer allows you to do some kind of cool things. So we don't really care what the physical size of your data is. So when you say like, okay, here's my block of data, it's 4K, instead of saying it's 4K, it's like, well, maybe it's 1K, maybe it's 2K, maybe it's maybe it's 6K. Like, I don't care. Like, just give me the data and I'm going to store it. So that's something that we put in there to give us some flexibility on what we're actually storing on the media, because we're doing the indirection ourselves. The media doesn't care. The media is just going to see a stream of bytes. The other big one, and this is where if anybody here has developed a file system before, this was the thing that made us all cheer, was we're minimal features, no namespace, absolutely no namespace, right? Because the overwriting rename between directories, and like that is the stuff where nightmares happen, right, for software developers, right? Because there's some weird locking problem, and it's like, oh, and then this thing tried to do that before this, and meanwhile someone was trying to write while they had a file lock, and like none of that stuff exists in this. Because we have a single consumer, which is that one layer that's above us, or one layer that is split to two, and we can basically go to them and say, yeah, don't do that, right? Here's your ID. Everything is like a GUID or a UUID, right? Like, identify this thing, and like, well, we want to do this, and like, no, don't write that way, write this way. And so that really gives us a lot of freedom to focus on what the system actually needs to do, which is provide these features and not try to be an all-purpose file system for the world. So this is kind of our, sorry.
Quick question on that stuff.
Yeah.
For ZNS.
Back here?
Yeah. Are you using the append command?
The append command.
So that's an unusual command compared to everything else in storage, where the address goes back to your indirection.
Oh, no. We are not doing that. Okay. That's not the point. Although, I mean, when you say not, as of right now, no. Tomorrow? I don't know. Maybe it could happen. But no, because what we're actually synchronous. So, not to get into, but the plan is basically we do have to send an order. The drive will tell us if we do it wrong, and you have this potential race where you can basically be in an asynchronous system. We've sent these two, and if one happens to get there before the other, then you could get an error, and so we're just like, all right, well then just do it again, right? Like, that's because the problem with append is, for our particular on-disk format, which I'm not going to get into today, just to be clear, but for our particular on-disk format, you have to know where you're writing, and so you have to have the address of where you're writing in the buffer that you're sending. So yeah, append is an interesting one. Like, I used to work on NTFS. That was like my thing way back when, and we had append as like, you can append to the end of the file. I don't know of anybody that actually used, I'm sure somebody did, but like it never, no bug was ever filed of like, yeah, we're appending. And if it did, I was like, really? Someone's using that.
Like a good idea.
Exactly. Yeah, exactly. I mean, it seems logical, but then when you actually go to use it, you're like, how am I going to use this? Yeah, so this is kind of our high-level architecture. We have the new thing is the yellow box. We have our consumer and our media underneath, which are outside of this. So far, this has worked really well. So we have our request processing engine, which is this engine that doesn't really understand media, and it doesn't understand how to store anything really anywhere. It just routes requests. Like, you want to write data to this thing over here at this offset or whatever. Like, it's the thing that moves everything around. And then we separated out the obviously in memory versus on disk, because sometimes the way you want to represent something on the media is very different than the way that you want to represent it in memory. So we also then have a separate piece that understands how to do those translations. So when you're about to send something down to the media, you ask the thing that knows how to talk to media, go parse this from the media. And then when it does, then it sends it down to the media. When it comes back from the media, you send it over that and say, go put this in a in-memory representation. And it may do nothing. I mean, it's possible that that particular data structure doesn't need to change. But it also does things like check CRCs and things like that, make sure that we haven't corrupted anything in the process. The media abstraction layer is a key piece of this. And That's one of those things that evolved a little bit. When we first started, we're like, oh, we'll just have this little thing that abstracts the media. But then it kind of became an entity of its own because other people were also like, well, this could be really useful for me, and I could use it. And it's like, yeah, having this thing that just says, okay, whether it's a conventional HDD, conventional SSD, an SMR HDD, like all of those things are abstracted from you. And to be clear, it is not doing indirections. When I say it's abstracted, it reports back the properties of the drive in a generic way. So instead of saying this is a ZNS drive, it basically says this drive has erasure units of this size that must be written sequentially and can get smaller as you're writing to them and things like that, right? And it's like, oh, that's like this. And the SMR hard drive might return that exact same information. And so it would use them the same. But then when it comes to things like I said, seek penalty, right? Okay, well, I can have, n write pointers on a ZNS. I can have, m write pointers on an SMR HDD, but I might not want to use that many on the HDD because it's going to cause the head to have to bounce around. I may only want to use one at a time, things like that. So it just abstracts that so that the other part, the request processing engine, these other layers, they don't need to even worry about the media. They get those properties and they just use that directly. And so this is, for me, kind of the key piece. This was like the aha moment when we kind of figured this one out. So the kind of at the bottom, we have our zones. And again, the zone could be a band on an SMR HDD. It can be a ZNS zone. We have this like multi-object append-only log thing. It's not a log structured merge tree, but it's kind of doing that basic logic where it's saying like, I will always write to this media sequentially, but I can, on top of that with the, I can do indirection for you basically. I can, allow you to update things in place. So our update in place system can create objects, data and metadata flow through that indirection layer and this multi-object append-only log and then out to the ZNS zones. And so this is basically us effectively moving the indirection layer out of the media and putting it up into our own system. A quick question?
Yes, is that on the same system or is that conceptually on, for instance, a system?
Nope, this is all the same system. The question was whether this is the same or different. This is all one system. This is like one node. Sorry, not like this is like running on one machine. And so yeah, these are that. And think of this. This is actually on one media device, right? So this is like one media device that has 6 zones or whatever. So our append-only objects, they're going to write their metadata to that same thing. I want to create this object, it's this big or has this ID or whatever that stuff. That goes to the same thing, but its data then can go directly to one of these zones because what the append-only objects are basically saying somewhere higher up, we have that other indirection layer. We have a log structured merge tree way up there. And it understands all this. It's always going to be appending and writing sequentially. And so I don't want you to do anything underneath there. So then it just maps your object directly to one of those zones, one or more of zones, and then says, I'm just going to write. So the data then just gets written directly to that. So that is, quite frankly, kind of the key piece of this. And then we can do all kinds of fancy things with garbage collection and stuff because we're like, hey, we know about these objects. The other piece I kind of forgot to mention on the previous slide was that the other advantage of doing this is when we do our garbage collection, the garbage collection of the drive is great. I don't want to misrepresent that, but we have additional information about objects. Like this object, I know its lifetime is going to be really short. This object, I know its lifetime is being really long. And so we can do things when we're doing garbage collection to optimize those things. So the next part here is our new development platform. This isn't really storage specific, so we'll focus on the D instead of the S in SDC. One of the things that we realized recently, some of you may have known that we recently got this company called Fungible, which has a DPU. It's a really cool product, and we're starting to go do things with that. And that led to an interesting problems for us of like, hey, this is a different programming environment than CPU. So we're doing some new development here. How do we make all of those work? So We came up with this new work unit-based development environment. It's inspired by the DPU, and by inspired, it was kind of like forcing function, because it's like, hey, you guys have to work on this DPU now. It's similar to SPDK, DPDK, for anybody who's familiar with that. Break your work up into chunks and schedule it out on things. Big piece of it is it abstracts the underlying platform, though. And this gets back into, we're saying, like, the efficient media utilization. It's also efficient development. Is if we have to write an append-only system, and I have to write an update-in-place system, and I have to write for a CPU and a different platform, a DPU, or I have to write for multiple, silicon types, we start getting this giant matrix of things we have to develop. So that's why we were trying to get into one storage system that can work for both of these, and then also one code base so that we can actually write once and compile that runs optimally. A key piece of this is it generates very different code that is optimized for each platform. And a key piece of that was we had to represent mutual exclusion in a unique way, and it had to be abstracted. Traditionally, mutual exclusion comes from, I'm going to grab a lock, or I'm going to go make that core the thing that does that. Those are usually the two ways we do things. On some platforms, grabbing a lock is super efficient. On other platforms, it's not. And then on some platforms, scheduling is super efficient, and on other platforms, it's not. So we abstracted this out. And it also allows for us to just do it in unique ways. And I'll give you a little teaser, because we're not going to talk about it now, but maybe at some talk in the future. We actually came up with yet another way to do mutual exclusion that's even more efficient. But that is for another day. But it just allows us to separate that from how the developer has to write their code. And it forces the developer to break up logic into pipeline stages. So it's basically like, do this, then do this, then do this, then do this. And it kind of moves along through the pipeline. And that's how we get like parallelism. And this whole thing was designed for massive amounts of parallelism. We basically wanted to have lots of little things running across many cores. And this is where I will go on my little tangent, which is the computing industry for a long time was, I have a core that keeps getting faster, 33 megahertz, 63 megahertz, 100 gigahertz, and then it gets up to, like about 4 gigahertz, I think. And we were like, yeah, this isn't going to work, right? Like, we're going to need more energy than the sun can produce in order to go much farther. So heat, all that stuff. So we said, okay, let's have lots of little cores. And that shift happened, but the development model hasn't changed 100%, I would say, with that. We still kind of think of like, I'm writing this code and it's going to run on a thread. I'm going to grab the locks that I need and do these things. And it's like, and when you have like 4 cores, it's probably okay. But as we're getting into like hundreds of cores, right? And I think the GPU world made that shift really well. It's like, we have thousands of cores, right? So they had to do it. I feel that this is that inflection point right now. So we are now moving into where we have to get into that same mindset. So it tries to strike a balance between coarse and fine-grained locks. So coarse locks, the coarsest lock is, I have the lock, right? Everything grabs the lock, and then it does what it needs to do, and we're basically just single-threading everything. On the opposite end of the spectrum is, I'm going to go lock-free, but there's nothing that's lock-free. It's always an interlocked compared exchange, and we're going to do that 10,000 times until we finally get through what we need to do. And so those are like the gamut of locks. So this thing tries to find that middle ground, which is you have some mutual exclusion, you do a small amount of work, and then you move on. So more than one operation, but not the lock. We also only provide one level of mutual exclusion, which is a little bit limiting, but it actually, so this is my other little thing about developing. I need to grab one little bit of water here. I used to think that and I'll include myself in this, I used to think developers were lazy, right? It's like, oh, take the easy way out, right? But then I realized, like, we're not lazy. We're like electricity. We go towards the path of least resistance, right? And so it's like, oh, I can just do this. I can just do that. So there's been this effort of like, I'm going to try to make development easy. And for me, it's like, I don't want to make the right thing necessarily easier. I just want to make the wrong thing harder. And so if you make the wrong thing really hard to do, the developers will do whatever they need to do to get the right thing to happen then. So that's kind of the mentality we've been using with this is we're not trying to make it too hard to do the right thing, but we're focusing on try to limit the wrong thing, like try to make it, really hard to do the bad thing. So you basically get one level of mutual exclusion. It's like this thing, run this, with this exclusion. Anything that uses the same mutual exclusion object, they all will run exclusive of each other by definition. And that's it. Like that's your primitive. And you can potentially build some more complex ones on top of that. But by doing that, it really, allows for like, say, this massive parallelism. And I'll show you an example of that. So this is what I'm just calling like linear code. This is like old school, right? So we want to write to an object. So what are we going to do? Well, we're going to lock that object. So nobody else can touch my object, right? And then I'm going to create a write buffer or whatever it is. I don't know. Does something based on the object, pulls fields out of it. And now I'm going to lock the device because I don't want anybody else touching this device because I'm going to go do an append, right? I want to write to the end, and I need to know that I'm the one writing to the end of it because if anybody else tries to write to the end of it, I'm going to get an error. And so then I find out where that offset is, and then I'm going to update my buffer with that offset and some other things, and then I'm going to actually do my write. And I tried to do this in color code. So like we have one lock, then we get the next lock, and so now this is like double locked here in the center, right? So nobody else can do anything to this object. Nobody else can do anything to this device. And then my write completes, and then I come back and I say, okay, somebody else can use the device, somebody else can, I'm going to update my object with some little thing, and then somebody else can use the object. And so this is the way we all write code like this, right? We've all done this. And it works, but then when you start really scaling up, you start running into problems. And so then usually the first thing we do is we're like, all right, I'm gonna be a little bit more creative. And we just do this, where we say, all right, I'm gonna lock the object, I'm gonna get my buffer, and I'm gonna lock the device because you know what the offset is. And I'm gonna get the offset, and I'm gonna update my buffer and get all that ready. But now I'm gonna release the object. So now somebody else can come in and they can touch that object. So you get a little bit of parallelism, right? But if they're going to the same device, it's just like a funnel, right? You have all the objects and they're all going to go to the same device. You're just going to grab it again. But it's a little better, right? Like maybe someone else wants to do something to this object, do some query that doesn't affect the device, and so they're able to do that. So you unlock the object. Now we only have the lock for the device. We do our write, and then we unlock the device, and now we're back, and then we re-grab the lock, and this is where we all made the same wrong bug where we say, oops, I'm going to grab the lock again without unlocking the device, and we get a deadlock, and you have to debug that one, and then 3 in the morning, and figure out why your customer is upset, and then you realize you had to like drop the device lock first. But so this is the typical thing of how we write code. This is the new way that we are doing, and I don't know, this may be a horrible representation of this, but it worked. It made sense in my head, but I'll just walk through it here. These are like our work units. So this is our write to object, which has some steps in it. And each one of these is a separate entity that's going to run somewhere. The color coding is just the mutual exclusion. These are exclusive from each other. That's exclusive from each other. So the way this works roughly, and I'll walk through this. Oh, nice, a little bit off. We're right here, which is this, create write record buffer thing, right? And so we do that. The way the system works is we actually have like this stack thing where you say, I want to push into the queue the work that I want to do. So I push into there, I'm going to update the record with the offset, and it's a stack, so it pops opposite. So I want to do that, but in order to do that, I have to get the offset that I want. But this is on the device. So this is in something else. So I do that, and then I'm done, and I return. And what happens is it says, okay, well now I'm going to run in the context of the device. So I'm mutually exclusive on the device, so I can get my next offset. So this is a standard, whatever the next offset is, I'm going to get it. I'm then going to update it based on the length, and then say, okay, I'm done. So then we had pushed the update record with offset before we did this get offset. So after that, it's going to go jump to that and say, okay, we're actually updating the record with the offset. So we go there. It actually updates that, and it says, okay, when I'm done doing this, I want to update my object, whatever that is after the write, and then I'm going to actually schedule the write. And so it schedules the work of like go write to the device. And then here's where we had to write a little bit of extra code. And this is where it's just getting people out of that mindset of instead of just saying, I'm going to lock the device and nobody can do anything. Because we locked the device to get the offset, but then we let go of that mutual exclusion. Somebody else could have gotten a new offset. And then we're now saying, I want to write. Someone else may be trying to write, and this is a multi-threaded parallel. So like they may have raced and gotten there first. So somebody may have come in and said like, I'm actually want to write, but I'm further ahead and I'm going to get an error back from that drive. So we had to add this code that basically says, well, is this one really the next one we want to do? And if, let's say the answer was no, it's like, okay, I'm just going to queue this one, right? I'm just going to stick this in. I can't actually do it yet because I know somewhere in this system is that other work unit that's flying through and I'm going to see it. And then that one comes through and it's like, I am the next one. And it's like, okay, then we're going to go ahead and actually do the write now. So this is that, just kind of changing your thinking. And it's not that hard, obviously, to do. And by forcing people to say, like, well, you can't hold the lock across those two operations, so you're going to have to solve it. They will, and they do. And that's the solution. And it's not that complex, but we just had to write a little bit extra code. But what this allows for is everybody can be like, writing to the object, getting it, doing things, these little snippets of code are running, they're going to the device for all different objects, for all different things, they're getting offsets. And the other thing is the system is generally designed to run things in order, so this generally won't happen. There are certain cases where we actually even guarantee ordering, but this is just in case it doesn't follow the order. And so then when that was done, it's like, okay, I'm actually gonna go do my update, and update the data and say like, okay, whatever I had to do, and that goes back. So that's the new model that we're using for development. And to give you another kind of higher, this is like now zooming way out. All of this code that we're talking about, it's just a whole bunch of these work units. And a work unit is just three things. I want to run this function, I want to have this mutual exclusion, and this is my context. And so and any two things that use the same mutual exclusion are kept from running at the same time by definition, otherwise it wouldn't be much mutual exclusion. And if they, but if they are separate, if they are using different mutual exclusions, I probably should have color-coded two different ones there. If they're using separate mutual exclusions, then they can run simultaneously, right? So that's it, that's the whole primitive. But the key part of this for us is we have two different silicon types that we're using here. It could have 3, 4, like whatever you're trying to run on, it is a completely separate compiler. It is not like we are trying to generate like one binary that's gonna run it. It's a completely separate compiler. It generates a completely different binary that is optimized for whatever silicon it's running for. And how it actually guarantees that mutual exclusion can be radically different and is radically different between the two systems that we're doing. But the developer actually writing the code doesn't even have to think about that. They are just given the guarantee these things will never run at the same time. So we'll just wrap up here. So having our separate systems provides robust product offering, right? We want to be able to give customers files and queues and tables and all these different things and the ability to store data in all kinds of different ways. And for us, that kind of distills down to like we update in place and we have append-only, but converging the key areas really reduces costs for us. And the key areas here is the media usage, right? Saying like, okay, I don't want to have two different systems that know how to talk to this hardware. And I don't want to have two different code bases for SMR versus ENS. And I don't want to have two different code bases based on the silicon type that I'm running on. Like, so by finding all those similarities where we can, and converging them, but also having the separation where you need to. I can turn indirection on and off so that when indirection's on, then I actually can do update in place for this system. With indirection off, I can do append only for that system and both get the efficiencies that they need. And abstracting the hardware reduces code duplication. And again, this is both for the type of media, SMR and ZNS, and kind of abstracting that so that I don't have to write those code bases separately, and also for the silicon type. Saying like, okay, I don't have to have two different code bases for these very different platforms, I can have one. And so this is just our vision for what our future looks like, and we're well on our way there. We have our append-only system, and by the way, these are separate systems now. So we have our append-only system, our update-in-place system. I have silicon type A running on some node. I have silicon type B running on some other node. Both of those systems can talk to either one. There's this common development platform. I did do different codes because they are very different implementations on those silicon, but the code that runs inside of them, the binary is different, but the code is identical. So that new object store code across both of the actual C code is identical. but it gets compiled for each of those platforms. And then I've abstracted all of the different hardware types: conventional HDD, shingled magnetic HDD, conventional SSD, ZNS SSD. That's all abstracted out. I can use all of those, and whatever makes sense for the system that we're installing, we can plug that in and it'll work. So that's the system that we're building. Like I said, we're well on our way, and so far so good. So with that, I will switch to questions, and Mata will join me up here. Oh, thanks. You were first.
You had some links, are you going to post these slides?
Yeah, so the question was about if the links will get posted. I think so. Like I sent the deck to SDC folks, so then I believe they put those out. So yeah. Yes, I put them up there, so they should be there. We'll make sure it happens somewhere.
So you were earlier talking about layering of indirection there.
Yeah.
And how you affect law.
Yeah.
So I was wondering, you have already used DNS SSD, which doesn't have indirection layer. So FTP drive also offers not of just one. So can you consider using FTP drive, and how does
Do you want to take that?
Sure. Yeah.
fit
Yeah.
in this picture? Or could you design the same system using FTP drive?
Sure. Sure. Yeah. So this is a good question. Basically,
Oh, the question was, could
Yeah.
we run on FTP drives as well as ZNS? Because you can do the stuff on FTP.
yeah. So the answer is yes. Short answer is yes, basically. But what we do is that when we started doing the design for ZNS and kind of how do we move towards a point where we have ability to handle how do we place data on the flash, basically, right? And so there, FTP and ZNS basically both provide us ability to kind of figure out and kind of control where data is placed, basically. But FTP has certain kind of interactions, like Garrett said, which is still allowing you to write in place, and it is going to allow you to say that, you know what, if I don't do optimal placement, I will still be able to do everything else that I need to do as well. It might have more WAF, basically. So the WAF in FTP is more variable, and it depends on the application above, its pop property as well. And the other thing is that FTP still has kind of, it has the table for kind of logical to physical translation. So they have DRAM requirement over there, and they also have things for spare NAND over there to keep the NAND capacity basically constant throughout the life of the device as well. So all those things basically still keep the FTP a bit more, I would say, resourced compared to ZNS as well. So that's why we are preferring for ZNS basically right now, because ZNS gives us the best ROI point of view basically, but we can still run on FTP if we need to as well.
I would also add that SMR doesn't have a FTP equivalent. And so since we run on SMR, we have to do all of the work anyway to work on ZNS. So since we had to do all the work anyway, we might as well just use ZNS because it doesn't have it's a cheaper drive. And so it's like, well, we'll go with the cheap, because I had to do it. If I didn't have to go do that work, yeah, maybe that's a valid thing, but I have to do that work. I'm not gonna get out of it.
So you're looking at maybe removing the dependence on zone descriptors?
Sorry, go ahead.
Zone
You're
descriptors.
looking at removing the dependence of zone descriptors?
When you say zone descriptors, you're talking about ZNS, and each zone has a metadata attached to it, actually. Is that what? Okay. So the question was that, are we going to use the zone descriptor attached to each zone, actually, in the ZNS pack or not, right? And yes, so basically, the MAL layer they talked about earlier, actually, that layer is actually trying to use everything available in the physical media, actually, and try to figure out what is the best way to use that feature, right? So for example, if it is a SMR drive, we are going to use CMR to do our metadata management at that level. And same thing for ZNS. We have a zone descriptor, actually, which allows you to store some bytes. Right now, it is 64 bytes of data, actually. And we are going to use that to maintain whatever metadata we want to maintain for that ZNS device. So yes, we are going to use zone descriptor for its purpose.
The relevance is that is a read modify write for the SSD.
Mm-hmm.
So that it's not, that's contrary to all your prior statements. So I was,
I'm sorry. So the ZNS device, actually, there is as part of the ZNS V1 spec, we kept that kind of piece of data for each zone, actually. And the purpose was that we want to use that descriptor to kind of avoid any more kind of additional metadata management at upper layer as well, right? So yes, so we have the devices right now which give us the descriptor. We can use that. If you don't have the descriptor, we can also kind of work without that as well actually, right? So the spectrum of the new object store we talked about is kind of fully kind of from SSD conventional to all the way to purely append-only system as well. But we will use whatever is available to us.
So I'm going to be respectful of the next speaker, so we're going to end there. We'll still be around if people want to chat and stuff, but really appreciate you guys taking the time to discuss.
Thank you.